Okay, so today's speaker is Miguel Zilhão, visiting us from University of Aveiro. Miguel received his PhD from University of Porto and University of Aveiro, and then did postdocs at the Rochester Institute of Technology, University of Barcelona, University of Lisbon, before returning to University of Aveiro. He is expert in computational physics and black hole physics, and today he's going to tell us about dynamics of black holes and scalar.
Recording in progress.
Thank you.
All right, thank you very much. Okay, so yeah, let me start. Is it working? Sorry. Or is it feedback? Right. So yeah, thanks a lot for having me, and in particular to Yasaman for hosting me and organizing everything. Yeah, so my name is Miguel. I'm a researcher at the University of Aveiro in Portugal. Yeah, I've actually been to Dublin quite a few times, but it's my first time here at DIAS, so it's great to be here. And for today, I would like to tell you a little bit about what has been one of my interests in research, and also the group over there in Aveiro, which I gave this relatively broad topic of dynamics of black holes and scalar fields. So I opted to motivate and try and go a little bit into some of these topics that we've explored, rather than going into a lot of details. But of course, if there is interest in any particular thing, we can discuss afterwards. Right. So let me start with some just very brief motivation, which is, of course, that from observations, it seems that there is a good portion of the universe that is unknown. This is what we've been calling the dark energy, dark matter. But there is, we've accumulated significant evidence for the existence of this dark component, of this dark matter of unknown nature and properties, which seems to interact gravitationally. At the same time, we by now have accumulated evidence for the existence of black holes, or maybe I should say, to the existence of objects that very much behave as we expect black holes to behave. I've added this plot here, which maybe it's even out of date by now, but so this is one of the, this is what they call this the stellar graveyard.
Excuse me, what are the axes there?
Right. So here, so if we, let me see if this is interactive. Yes, it is. So here we have in solar masses, right? So this is how you should read these things. So in blue, these are the black hole events that have been detected by LIGO Virgo, right? So for instance, you can see the cursor, right? Yes. So for instance, this one here. So there was, so it's an event that was generated by two black holes, one of 14 solar masses, the other one of 7 solar masses, so that's the 7 and that's the 14, and the final one is so the merged. So after merger, this originated a black hole of this 21 solar masses.
Yeah.
This now. Right.
So what are the axes?
On the x-axis, I don't think there's anything in particular. This is just a bunch of all these scattered events, right? So the important axis is the y one, which is the mass of each of them in. Yeah. So yeah, so the blue ones are just all the events that have been detected, and the black hole events. So yeah, I mean, now these detections are more or less routine. So we have decent evidence to the existence of these objects, or at least to the existence of objects that pretty much behave as we expect black holes to behave. Right. But then going back to dark matter, so we can expect that this component, this dark matter component, that makes up a significant fraction of astrophysical environments, that can lump together and form structures by itself. Indeed, one can model that there are different models for dark matter. Of course, one of these possible models is one of the simpler options even is to consider it to be some sort of scalar field. Sometimes this goes by this name of the fuzzy dark matter or scalar field dark matter. And for the purposes of the perspective that I will take here, that's precisely that's precisely. So I will take from now on just the perspective that I will consider this action here. Yes, so this action here to be my
Somebody trying to ask.
What is that? Yes, good.
What are you going to do now?
He can unmute himself. But at least he's muted. He's not. He's doing something else. Yeah.
Well, anyway, so I will take this perspective, right? So from here on, we'll just consider that we have this model, which for our gravitational system, whatever. So we'll consider this to be our action, which is
Any reason for choosing minimal update?
for simplicity, really, just that. It's yeah, just simplicity. And we'll continue with this from now on. Now, oh, and I should say, yeah, I mean, it's not it's not what I will be presenting, but yeah, there's been, from my understanding, cosmological simulations that use this sort of modeling, this fuzzy dark matter models, that apparently reproduces quite well the stellar formation and all the structure formation, sorry, throughout quite a significant number, a decent number of length scales.
What's the significance of you were writing the word fuzzy there? Are you going to consider fuzzy dark matter or not?
For my purposes, not so. From these purposes here, not necessarily. So I'll just fix some mass for the scalar field. This is just, you know, for as possible motivation. But for the results that I'll show, this won't necessarily be fuzzy dark matter. But anyway, so with this action, what we're doing in a way also, it's to enlarge the solution space, right? So from here on, we no longer have just the vacuum solutions as our solution space. We now have not only black holes, but also in particular boson stars as possible compact objects. And so boson stars are compact stationary configurations of scalar fields, of a scalar field bounded by gravity, and they can actually form. So it's been shown that they can form rather generically as a consequence of gravitational collapse. They can take many shapes or forms. Of course, the most typical, let me say, boring configuration will just be a spherical boson star. But one can also construct other kinds of objects. So with different sorts of dipolar structures. So I'm showing here just one such example of what we named this dipole boson star. Now I should say this is we're considering a complex scalar field. So this has a real imaginary part, and this is more or less, this is an animation. there's much, but this is an animation of the evolution of the real parts of the scalar field in one of these dipolar boson star configurations. This is something that can be constructed numerically, and indeed the group over there in Aveiro, in particular, Carlos Aveiro and Eugene are experts.
So you're talking about a charged scalar field.
It can also, one can also charge them. Yes,
It's complex.
It's complex. It's complex, but we will not be charging them. One can, but I will not be talking. So not for the models that I will be considering, but one can in principle charge them.
No, wait a minute, I don't understand. You are considering charge ones, or you're not?
I'm not. One could in principle.
What is this picture showing? It's just an oscillation.
Yeah, this is just the real parts of the scalar field as a function of time, right? It's really just so it's really just this is the typical harmonic dependence.
Yeah, but I'm very thick. What am I learning from looking at that?
Not much. Just how it behaves. It's just a visual aid.
Okay.
It just because so I mean this is something that's constructed numerically, right? So I can just I can show you an analytic form for this this radial function. So I'm just showing the video of how it behaves. Yeah. Okay, so there's that. Okay, so there are different ways that we can try and study the interaction between black holes and scalar matter, right? So okay, so I've been motivating that. I was motivating that.
I'm confused as to why there's time dependence in that solution. I mean, because since it's not really a charged one, it's just two real scalar fields.
It's two. You can think of it as two real scalar fields.
Why is there a time dependence between the components of the two real?
Would
expect that to be.
So for this model, for this model, the trick here is that the stress energy tensor, because the stress.
So this is a real scalar field.
This is a complex scalar field. Yeah, it's
there's a bar.
There's a bar here. Yes, there's a bar here, and this is the So this is a complex scalar field, and so so what will happen is that in the stress energy, so as you couple to Einstein's Einstein's equations, R mu nu equal T mu nu, let's say, right? So what will end up showing on the right hand side of the equation, so the T mu nu, it will not be time dependent. This is the trick for some of these constructions.
T mu nu, is it time independent?
It's time independent, yes.
But you are saying that you can still put in a rotation between the two components of this.
Because with this simple, it's just as simple as so it's exactly what it's there, right? So that with this kind of time dependence, when you multiply it by its conjugate with its complex conjugate, the time dependence goes away, right? So this is the trick to the construction, that from the point of the Einstein's equations are not seeing this time dependence. But the scalar field itself, the real part of the scalar field does have a time dependence, and so does the imaginary. But they are such that they precisely cancel, giving you say, if you want, the density of the field that will then be what the Einstein's equations will see. This does not have a time dependence. Right. Yeah, but so again, this is a solution that one can construct exactly, if you will, even though, of course, it's numerical. But yeah. So other things that one can do with these kinds of model is study the interaction of black holes and scalar field, scalar matter. Right? So I was motivating that we have black holes that we can create, we can model our dark matter with scalar fields. So obviously we can try and study how these two objects would, how these two systems will behave dynamically. And this is what I will try now to, and this is what I'll be discussing from now on in two different regimes. Now, one first thing that one can try and do or study is just the Klein-Gordon equation. So, okay, so this will be one first approach to study interaction between black holes or in particular black hole binaries and scalar fields. What we can do is, instead of solving the full coupled system, what I'll be showing first will be just solving the Klein-Gordon equation, so here, but on a dynamical metric that I'm going to model it, but using the lowest order post-Newtonian approximation for a binary. So essentially, what I'm trying to depict here in this picture here. So I'm setting my two black holes that will then be orbiting around, and on this background, I will solve the Klein-Gordon equation, and which will not backreact, right? So the metric will not see the scalar field, but the Klein-Gordon equation does see the metric, of course. Okay, and this is an interesting case because it's relatively simple to study perturbatively, so in a semi-analytical way. So I can write my metric to the lowest order in the post-Newtonian expansion, something like this. And then, so I take this metric, I plug it on the Klein-Gordon equation, and in its non-relativistic limit, what the equation that I end up getting is essentially a Schrödinger-like equation with this kind of Hamiltonian. And if I solve for that, I can solve for this in how I would solve for any quantum mechanical problem. So I can get the spectrum. So essentially, what I got was I've reduced my system to the Schrödinger equation in some sort of ionized dihydrogen molecule. So this is what it. And I can solve the eigen for these frequencies for the energy levels of this system. What I can also do is compare what I get with a numerical simulation of this of such a system, and this is what I want to show. Put this a bit back. Okay, so what am I showing here? So what I'm showing here is a numerical simulation. So a numerical simulation of what I was just saying before. I have my two black holes orbiting around each other. This is fixed, right? So I'm fixing this. I'm prescribing, in a way. I'm prescribing this metric, and I start with a spherical blob of scalar field around the binary. And as the system evolves, let me push it back. So I start with this spherical shape of scalar field, and as the system evolves, naturally, the system relaxes to a configuration where I get precisely this molecule-like configuration that very nicely matches the perturbative treatment that I was seeing before. Now I should say that this is not a static or stationary. This is not a stationary configuration. It's a quasi-stationary in a way. It's very long-lived, but it decays, right? So this doesn't exist as an exact solution, but it's very long-lived. So it's an interesting example that one can explore, and it gives us this very interesting connection with, if you want, with quantum mechanics.
So your system here is your starting condition. Initial conditions are spherical.
A spherical of scalar field. Yeah.
Field.
Yes. Yes.
In this background.
In this background, exactly.
And you're just following the evolution.
I follow the evolutions along, yes. So in a way, the initial condition even sort of, well, this is not exactly the initial condition. This is something that is a snapshot that I took a little bit afterwards. But yeah, I'm initializing everything, more or less, or everything. Then the scalar field cloud in a spherical way, and then the evolution takes care of the rest.
So you've taken a wave for your initial condition.
It's a
radial wave.
It's a radial pulse. Yes.
Okay.
Yes, I think so. We experimented with slightly different profiles, and the outcome didn't. I mean, yeah, there was a little bit of a difference on the evolution, of course, but say the quasi-stationary configuration that was reached didn't really depend on how we were initializing the system.
This configuration here looks like it's got some radial amplitude.
Yeah. This is not exactly at t equals 0. It's already a little bit afterwards. Yeah. Okay, so this is one first. This is, yeah, just one. Whoops, I moved a bit too far. Okay, that was one first study that we've done. Now, for the rest, I would like to where I'll probably spend most of my time is this work here, where we studied the collision between a black hole and a boson star. So what we decided to study was, or given this motivation that, I mean, there is this right. So given that there is this this motivation of dark matter, and given the existence of black holes, the evidence for that, what we were interested in studying is, and what happens when we have a black hole, say with very high velocity, piercing through one such configuration of scalar matter. So that's precisely what I will now explain. So we're going to consider the motion of a small black hole as it pierces through a large boson star structure. And
looks like the William Jellicoe.
They could, yes. Now, what I've been saying so far is well, let me say, the scientific motivation for this. But of course, there's another motivation for this particular study, which is that it's really a fun thing to do. I mean, in a way, is going hunting. It's going hunting with black holes, right? So it's a really fun project. So and that was also part of the motivation behind it. Now, so before I go into a bit, I suppose, of the technical details and the results, let me just say a few words about, I guess, what we expect to see, and to just say a few things about the phenomena that will be the important physical process behind the simulations that will show a bit further ahead, which is this effect of dynamical friction, right? So here I'm just depicting the typical dynamical friction approach of Schindler-Secker, right? So what's the picture behind all this? So we have, let's say we have a more or less uniform distribution of particles, right? So here in this top panel, and now we have this perturber, which will in this case, in our case, will be a black hole that will move through this this original uniform distribution. Now, as the perturber, or the black hole, is moving through this medium, it will of course disturb the environment, and one typically has something of this form, right? So the particles in the medium will rearrange themselves. And what will happen then is an asymmetric configuration where we have a higher concentration of particles behind the moving perturber than ahead, right? So this in turn induces that the moving perturber will feel more of a gravitational pull in this part here, so it will start to become pulled backwards. So the effect of this is something that behaves effectively as friction, and we will see then how this will look in practice in the simulations that I will show a few slides ahead. Now, so now this is the part where I'll say a few things about the actual technical details. Yeah, so let's go through those. But yeah, just to set the stage, I don't want to spend too much time. But if there's more technical questions, we can discuss. But anyway, so for this particular, so we'll actually consider two cases. One with a self-interacting potential, and the other one just. So we were on different configurations. I mean, here the most generic one that we did was with this kind of potential, so something that has self-interactions. But the main phenomena, we don't need the self-interacting term. So we can think of this as this potential really as only with the mass term is.
What is sigma? What is sigma?
Yeah, it's a tunable parameter. This is a tunable parameter that we can specify. I think in practice for the simulations that I'm going to show here, we're not using the second term. So if the sigma will be effectively infinite. For the
bracket is 0.
Mm-hmm.
Everything in the brackets is 0.
This one here.
That's all done.
So it will reduce just to the master. So for the simulations that I will show, we did run other cases with I think sigma equals to 1 or 0.5 or something like this. But for the simulations that I will show, it doesn't matter much. Okay, so now the point here is that we're going to solve this fully numerically. So before I was showing you this this perturbative approach that we followed, but now we're going to do the whole thing fully numerically. So I would like to just to explain a little bit how this is done for those that are probably may not be completely familiar with the formulas. So the construction is as follows. Of course, we start, as we always do, with Einstein's equations. Now, Einstein's equations, they are typically written in this form that everyone is familiar with, and it's very nice, it's very elegant, but it's also a bit deceiving, right? So if we were expand them out, so what we get is something like this, right? So it's a set of 10 second-order differential equations or non-linear coupled partial differential equations on geometric tensor. So if we want to do something numerically, so if we want to be able to give this to the computer, of course, our very first task is to recast these equations as something that the computer can understand. So in particular, as a time evolution problem. So the first task is to write Einstein's equations as a well-posed initial boundary value problem. Then, of course, we need to discretize, so we get a set of PDEs which we need to discretize. Then we need to specify our initial conditions, our boundary conditions, and also find a way to deal with the singularities if we are treating black holes. So in practice, so there are different approaches that one can do to accomplish this. One of the most popular ones, and the one that I typically use, is this so-called 3+1 decomposition, where the metric, so where we write the metric element in this form, which is just a particular ansatz. And writing the metric element in this form and plugging this back in Einstein's equation. So after a little bit of labor, what we get is the ADM York equations. Now, what I would like you to pay attention to is that these two equations, we have two sets of equations. We have a set of evolution equations and a set of constraints, right? So here, this set here is a set of equations that has explicitly a time derivative. So these are our evolution equations. And this set of equations here, there are no time derivatives. So these are just, in a way, algebraic constraints that need to be obeyed. If you're seeing this for the first time, this is very reminiscent of a set of equations that I'm sure you've seen before, which is Maxwell's equations, right? Even if they are, so for the ADM equations, even if they are more complicated, that they are nonlinear and so on. The fact is that their fundamental structure is very, very similar to what we have in Maxwell. We have, again, here as well, we have a set of evolution equations. So we have a set of equations with explicit time derivatives, and we have a set of constraint equations, so equations that don't have time derivatives. It's just constraints that, so elliptic equations that need to be obeyed at every time step if we are to be solving Maxwell's equations. So it's a very similar thing. It's just that the equations are intrinsically more complicated, but the idea is really the same. Now, there's a bit, well, quite a lot of other complications. I mean, in particular, there's the fact that the ADM equations that I just presented, they are not strongly hyperbolic. They are not a strongly hyperbolic set of differential equations. So one still needs to recast them in as a strongly hyperbolic system. But let me just not spend too much time with that. I mean, for the purpose here, I'll just say that we know how to do this thing. It's by now well understood. So that's the procedure. That's the procedures that we do. And in the end, we get a set of equations. So the ADM equations are weakly hyperbolic.
What does that mean in practice?
In practice, it means that if you diagonal, so the principal symbol doesn't have a complete set of eigenvectors, and this is bad for the point of view of numerical evolutions.
What's the origin of that? Because the Einstein equation's principal symbol is fine.
It depends how you write it, right? This very much depends on how on the formulation.
Does it depend on the lapse and shift you choose?
That too. It also depends on the lapse and shift. Yes.
So if you choose them carefully, then it should be hyperbolic.
It's not just about that though. It's about the evolution variables themselves. So in particular, for instance, there's one other formulation. So the generalized harmonic formulation, where you immediately get a set of wave equations, and this from the beginning, from construction in a way, is strongly hyperbolic, because what you get in the end is just a set of wave equations, and the wave equation is strongly hyperbolic. So that's one formulation. But this is not that. So the ADM formulation is different. It's not the generalized harmonic, and it has this problem. So in practice, it's not used for time evolutions. Let's say a rewritten form of the ADM equations is then used in practice. It's one of the most widely used formulations called this BSSN formulation, which is the one we use in practice.
I don't understand the logical structure there. So you're saying it's just a property of the ADM system?
ADM system.
So if there's another way of formulating it, it's just not this problem, then it's just like a bad set of coordinates. It's a bad system. In other words, what is the real evolution of the system?
So what we do is we precisely use this other formulation, this BSSN formulation, which is strongly hyperbolic. Now the only reason that I showed before the ADM system is that it's a much simpler. It's much simpler. So you get the intuition that you get.
So would it be fair to say that you're using the ADM, the York equations, they have a slight weakness, that they're not strongly hyperbolic, but that's something I'm prepared to put up with because it's simply work.
No. That was just for presentation purposes. No. What we work with is not the ADM.
Can you reformulate my sentence so that it makes contact with what you're doing?
So what we do is we rewrite so we don't work with the system of equations. In practice, what we do is we introduce a new set of evolution variables that complicates this, that introduces extra variables and dramatically complicates the how the equations look. And then that system is indeed strongly hyperbolic, and we work with that.
Oh, right. So you didn't need to worry about that.
Yeah, in practice, yeah.
Feel better.
Okay, so we have our set of evolution equations. So this we can code up on the computer. So then what we need then is some initial configuration to for the computer to then take and perform the time evolution. And this initial configuration then that we will use is just a superposition of the metric element of a boson star and a boosted black hole, which we want to pierce. We want it to pierce through the boson star, right? So roughly, this is how we build the thing. So this is the metric. So this here in the bottom is the schematic form of the metric element for such a boosted Schwarzschild metric. We superimpose that to the metric of a boson star configuration.
And you're just showing us the spatial part.
Yes, just the spatial part, because it's essentially it's all we need to set up the initial initial configuration. So what we do is we prepare the data on a hypersurface, and then the computer does the time evolution of that. So pictorially, this thing, it more or less looks like this, right? So we have this boson star with a given I think in practice, at the origin of our coordinate system, and we're going to start with a black hole far away, which will boost, and it will go through the this boson star. Well, this is what I was saying before. So for the evolution system, we use this PSSN system, and the code, the infrastructure is fully open source. So if anyone is interested, I can explain how to get the code and set it all up. And before showing the videos, I'll start by showing some of the snapshots. So I will show two different simulations with different mass ratios between the size of, with different ratios between the size of the black hole and of the boson star. So in this first, so this is what we call this 1B. The black hole has mass 1 in these units, and so there's the ratio between the size of the black hole and the boson star is 6. So the boson star is 6 times larger than the black hole, and for this one that we call 4B, the black hole is much smaller. So there's a ratio of roughly 60 between the black hole and the size of the boson star. So this one here on the left is this first case, and the one on the right is the second one. So I will be showing the videos afterwards, but just to prepare you, so you should be reading this from left to right. So we start with the boson star here at the origin. The black hole will come from below, so you don't see it here in these first panels. But as the black hole approaches, of course, the boson star will start to feel the gravitational pull, so it will start to move. And then finally, so here, this is when the black hole enters the frame. As it approaches the star, it will start to deform it. It goes through and ends up accreting all of the scalar matter. The same thing will happen in this other configuration. The difference is that the black hole is much smaller. So here, so the size of this purple circle more or less depicts the size of the actual black hole in the simulation.
It absorbs all of this.
It does, yeah, it does in both cases.
This is a slowly moving black hole.
It's going at more or less half the speed of light when we shoot it. So originally it goes at 0.5 of the speed of light.
When you said its size relative or its mass relative to the boson star was.
So in the first case, that's a factor of 6, and in the second case, it's a factor of 60, give or take.
6
Between the
larger.
the boson star is larger. Yes.
Looking at the total masses there, you don't seem to get the radiation.
Very little. So this plot here is for the accretion. So there is in both situations, even for the case where the black hole is roughly 60 times smaller than the boson star, the end result is that it accretes almost all, in practice, all of the whole of the boson star. Right, so given all this, let me show you some of the, before that, this is also interesting. So this plot here, this here plots the velocity. Or rather, the velocity is the bottom panel, and the top panel is the position of the black hole during the simulation. There's an interesting thing that I will try to point your attention to in the next slide, I think, during the animations, which is that there is a case where which is roughly here around 400, that the velocity of the black hole is negative for a very, very small amount of time. So basically what is happening is that the black hole is being tidally captured by the boson star. But let me then show you the actual animation. So this is this first case. So there we have the boson star here sitting at the origin. The black hole will come from this bottom part. There we go. There we go. So let me show it again. So the boson star will at some point start to move. It's not moving. Right. Yes. When the black hole approaches, then of course the boson star starts to move. Then the black hole comes and accretes the whole scalar configuration. More interestingly, perhaps this other scenario where the black hole is this is the situation where the black hole is roughly 60 times smaller than the boson star. So once again, the black hole will come here from the bottom part. So for now, nothing is happening. So it's not even gravitation. So gravitationally, the boson star it's not yet reacting to the presence of the black hole so far away. There we go. The black hole is coming. So notice here how it starts to move backwards, and then it goes on its merry way and reaches the rest of the boson star. So here at the end of our evolution, there's still a little bit of a remnant of the scalar configuration. Let me play this again. There's still a little bit of a remnant of the scalar field around the black hole, but what we expect is that asymptotically this will, if all of this will end up being accreted by the black hole. There we go again. So here's when the black hole becomes tidally locked to the star, and you can also appreciate that its size is changing, right? So in the beginning, so you see this is a very, very small dot that's getting a bit fatter as it accretes scalar matter, and then there it goes off on its merry way.
Can absorb all of the.
Yes, we were not expecting that beforehand.
What happens in the limit where that ratio goes to?
That's what we would. That was the thing we wanted to explore actually, and we were hoping that this would for this ratio of 1 to 60, if we want, would already be enough, because ultimately we were expecting to see for a large configuration of scalar matter that the black hole wouldn't just destroy the whole configuration, and indeed this is what it's expected, right? But we weren't able to see that. These were the.
Did you try faster moving.
We tried faster moving, and we saw essentially the same behavior. We would like to have tried with for an even larger length ratio, but this was as far as we could go for computational computational limitations. Already the simulations were quite demanding, so more than this we were not able to do. But indeed, that's what we expect. That at some point, the black hole will have to the scalar structure will have to be able to hold its own, right?
What computational power are you throwing at it? It's not just a laptop.
This is not just a laptop, no. No, we run this on supercomputers. So the same. I don't remember exactly on which machine we run this. Actually, as I'm speaking, let me just put the final remarks because I'm essentially that. But yes, so what we typically run the simulations in supercomputer infrastructures.
Okay, very good.
The system is a bound state system to begin with. Very interested in the energy. Just if I take them far apart, I can choose as a Newtonian system, and it's a bound system. The total energy is negative. The gravitational energy, binding energy.
The whole.
I suspect because it's ending up that way, and I'm thinking.
So I don't remember but because in principle one could ramp up the boost velocity for the black hole. So I don't know if it would necessarily.
You want it to be large enough that it was escape velocity, or higher than escape velocity.
In principle, I think one could set it up in that it's in the way that.
I'm wondering what would the escape velocity be for that system, because it looks to me like you've got a bound system. And once it's a bound system, well, it's going to end up in a state when the black hole swallows everything.
Actually, I don't recall offhand if we. I think we computed that, but I don't recall offhand. Well, that was it. So basically, yeah, just as a final slide. So I tried to motivate why we were why we're generically interested in this kind of systems, generically the interaction between scalar matter, bosonic fields, and black holes. So these were challenging simulations of boosted black holes and boson stars. So we were a bit surprised to see that even for these length ratios that I was just showing you of 60. The boson star was entirely accreted at the passage of the black hole. We were hoping that we would be able to see cases where the boson star structure would remain whole in a way, but we weren't able to do that for the computer resources that we had. We were able to simulate. So at the late time of this simulation, there's this gravitational atom that is formed. So it's essentially a black hole that's surrounded by a quasi-bound state of scalar field. It's essentially the remnant of the boson star. This is a quasi-bound state. So asymptotically, the end result will be that all of the scalar matter will have been accreted by the black hole. Why I think one can expect that for even smaller black hole masses, the black hole would pierce through the configuration without destroying the boson star, but this requires a very large amount of computational resources, which we didn't have. And of course, this is why I didn't mention this, but of course, all of this was for non-spinning and non-charged configurations. So if we were to spin and to charge the black hole, one could even have even new phenomena to explore. And this is it. Thank you very much for your attention.
Very interesting. I've got to go downstairs, but thanks very much.
Thank you.
This comes on the archive, is it?
Yes.
Under your name.
Yeah.
Okay, great. Thanks.
So what's the effect of the potential of the scalar field? Because you mentioned that there are several options for that. Does it do anything significant with the dynamics?
I would say that it doesn't do anything significant. So we were trying. So our part of our motivation to study also the self-interacting scalar field was precisely to see if we could do without having to go to such large length ratios and see a new phenomena just by tweaking the self-interacting term, instead of having to keep reducing more and more the mass of the black hole. But in the end, even if, of course, quantitatively the evolutions would be slightly different, but qualitatively it was the same picture.
Why do you actually expect the small black hole to be able to escape?
Well, it's always able to escape, right?
No, as in, like, without. Why do you expect a small enough black hole does not absorb the entire boson?
I mean, just from I guess if you think of, just for in the infinite limit, right? I mean, for super large boson star configuration or scalar field configuration, let's say, I mean, you could set it up in a way where, let's say, the end of the scalar structure isn't even in causal contact with what's happening, let's say, in the middle, right? So it would take a long time for the disturbance here to propagate all the way to the boundary. So in this sense, you sort of expect that the whole structure can accommodate. I mean, before being completely. So the propagation of this disturbance will take such a long time to reach the whole structure, so that we would be able to hold its own. But yeah, we're the kind of length ratios that we're able to probe is still really, really far from that regime. But just from continuity, we expect that's on that limit. This will necessarily happen. So at some point there would have to be some sort of transition. But we were not able to reach not even something that's close enough, unfortunately. Originally, we thought that we would be able to see it, but we were a bit naive, I guess.
We certainly would expect that black hole coming in from infinity, moving very rapidly through it, would not absorb everything. It would surprise me if it would absorb everything.
Yeah.
Just essentially from the reasons you're saying. Some of it would just not be able to receive the signal that it was being spoken.
Yeah. Yeah. Unfortunately, computationally, we're not able to reach that stage. But indeed, we definitely expect.
What's the difficulty with making the black hole travel faster? Yeah, you need a finer mesh for you.
Yeah, we need a finer and finer mesh, which implies more and more resources. But I should say that I think it was trickier for us to have having a smaller black hole was even trickier than having it moving faster.
Yeah. Well, I would think that you should try moving it faster. Because I think it should get through what it's moving faster.
Exactly, yeah. But still, it's still difficult to probe. I mean, I think up to 0.7 of the speed of light we were able to go. More than that, it started to be very challenging.
Another question.
You could also try different impact factors.
Ah, yeah, yeah. That would mess up the symmetry.